Welcome back. So we were talking about the FE exam manual, and we were going over different transportation topics from the FE exam manual. And I just wrapped up the topic on horizontal curves portion of the design. And that's right here, horizontal curve formulas. And I'm going to talk about the vertical curve formulas. Now, again, we haven't yet talked about the side distance because it's very important for us to understand these vertical curves form. I'm not sure. It was giving me some options of like just, so I'm going to start talking about the vertical curve formulas here. I just wrapped up talking about the horizontal curve formulas. And the idea of this is now that you're looking at the key difference between the horizontal curve and vertical curves is that now you're not looking at bird's eye view. You're instead looking at what we call the profile view. And one big difference now between the profile view and the bird's eye view that we were considering in the horizontal curve is that now when we talk about stationing and length of the curve, those things, in the case of circular horizontal curve, we discuss those in the form of along the curve, essentially. And now, but now in the vertical curve, we project these points onto the horizontal plane. And then when we talk about the length of the curve, that is that is figured from the projected distance along the horizontal plane. Okay? So when you talk about the length of the curve, that is the straight line distance, as you can see here. Okay? So that's how we measure the length now. We do not measure the vertical curve length along the curve. We measure it as a projected point onto the horizontal plane. And remember, on the horizontal curve situation, horizontal curve was the horizontal plane of the road. So that's something that we should keep in mind. And that changes on the stationing calculation, the way we do it, and so forth. So the idea is still the same, but right now, why do we need vertical curves? We need vertical curves because we are trying to figure out how should there be a change in elevation. Okay? So now what is going to happen is that we are looking at the profile view and you're navigating on this chart, you're navigating an upgrade. Okay, you're navigating an upgrade here. And then at the end of the curve, you're navigating a downgrade. And obviously, you don't want to be in a situation where roadway goes like this, and then there is a discontinuous point on the road, and then you have to make a transition, very sudden transition onto a downgrade. Obviously, that's not how highway design works. The way it works essentially is that you want to provide that smooth transition between going up and then going down at this point. So there is a G1 grade going up here in this figure, and then G2 grade going down. And anytime G1 is greater than G2, as is the case here, because G1 obviously is positive, G2 is negative, so you could say that G1 is greater than G2. So anytime that is the case, you end up with what we call a curve like this, a crest vertical curve. But if G1 is less than G2, if G1 is less than G2, okay, an example of that would be you will have G1 is a negative curve or a negative grade, and then you go up from there. So this is G1 going downhill, this is G2 going uphill, and we're not talking about the absolute values here. We're talking about whether the value of G1 is less than the value of G2. Okay, so not talking about absolute value, we're just talking about just the value itself. So if G1 is, let's say, negative grade, G2 is positive grade, we know for a fact that G1 is less than G2 because obviously negative number is less than a positive number. And the curve might look like this. The curve might look like this. And then that's the type of a curve that we call the sag vertical curve, SAG, sag vertical curve. Now, if G1 is less than G2, but the formulas that are listed here, they apply nevertheless the exact same way. Whether it's a crest vertical curve or a sag vertical curve, the design formulas that are given on this sheet, they work out the exact same way. Okay? Because they work out the exact same way, this is sort of, now, one thing to note is that I told you when we were talking about the horizontal curves, the curve connecting the PC with PT, in the case of horizontal curve, was the circular curve. Now, the curve connecting PVC, now obviously if you notice the trend here, or the pattern, we tack on a V in the middle. PVC, PVI, and PVT. So this is point of vertical curvature, point of vertical intersection, and point of vertical tangency. Okay? So we tack on a V in the middle, and then this is the start point of the curve, this is the end point of the curve, and the curve in the middle is not circle anymore. It's the curve is defined as a parabolic curve. Now, parabolic curve is interesting if you recall from your basic, geometry or algebra where you might have learned this. The equation of a parabola is defined as a quadratic equation. Ax squared plus bx plus c, you might have heard that equation. But if you look at what is so special about the parabola, is that if you take a look at the second derivative of the parabola, if you think about the second derivative of the parabola, so parabola itself is a quadratic equation. You differentiate it one time, so the format could be y equal to ax squared plus bx plus c. You take the first derivative, you get a linear equation. You get the second derivative, you get a constant. That is why we use parabolic curve to connect PVC with PVT, because the rate of change of slope is a constant. And that basically provides the road user with a comfort level, because the rate of change is not changing as you move along the curve. It provides a smooth transition because the rate of change of grade is a constant, and you are able to go from grade G1 to a grade of G2 at a constant rate. The rate of change is constant, and that provides for a smooth transition. Okay, so here are some, and that's just the answer to why we provide a parabola, because it provides a smooth transition between the first point grade and the last point grade. And basically what keeps happening is that you go from G1 at some point, and if you're transitioning between an upgrade and downgrade, at some point you hit the grade 0, and then you go to G2. Now, one thing that happens, the kind of curves we design is what we call the equal tangent vertical curves. Equal tangent vertical curves means that the PVI is exactly in the middle. So if you project a point onto the horizontal plane, if you project this point downwards, typically this length would be L over 2, and this length would be L over 2. It's not a requirement, but most curves that are designed are going to be L over 2 and L over 2 in this case, and we call them equal tangent vertical curves. Equal tangent vertical curves. Okay? So where L is the length of the curve. Remember, L is defined, as I told you before, the length of the curve is defined along horizontal plane. PVC, we talked about point of vertical curvature. PVI and PVT, we already discussed that. G1 is the grade of back tangent. Okay. G2 is the grade of forward tangent. Okay. X is the horizontal distance from PVC. And again, X is not measured along the curve. X is measured along the horizontal plane. So it's kind of like you can define that as a coordinate system of sorts. So your X's are measured along horizontal plane, and Y is measured as the distance between the initial tangent and your curve itself. Okay, initial tangent and the curve itself. So your curve's equation in this case is given as y equal to ax squared. Okay, y equal to ax squared. And then we also call it, if you go back and look at your notes from your fundamentals of transportation engineering class, you might find that you learned a different equation for this. You might have learned the equation of the form y equal to ax squared plus bx plus c. And that's your traditional quadratic equation form. And that's what you might have learned. But this y equal to ax squared is what we call the offset form. So this is the offset form of the equation. Y equal to ax squared is the offset form of the equation, where small a is defined as g2 minus g1 over 2l, g2 minus g1 over 2l. Now, what is that actually? If you think about it, what is this a? This is the, if you look at the g2 minus g1 over l, g2 minus g1 over the length of the curve, that is basically that constant rate of change of the grade. And then you divide that by 2. So this is basically half, this a value, the small a value is a constant that is equal to the rate of change of the curve and half of that. Okay? And then you could figure out other things that might be in there. E is equal to, so let's look at x is the horizontal distance, g2 is the grade of the forward tangent, basically the end tangent. A is the parabola constant. I told you already how that's defined. Small a, g2 minus g1 over 2l. Y equal to tangent offset. Now this y value is always defined from the initial tangent. So I will always define y. I will always define y from the initial tangent. So if I want to figure out what is the y value, I'll have to sort of define. So this y value always keeps going up. So my y value past any point past the PVI would be defined based on this distance right here. Okay, so just want to make that clear, is that my y value past the PVI is not going to be defined from this forward tangent. It's always going to be defined from the initial tangent. So one thing I want you to note here is that when I say tangent offset, it's always relative to the initial tangent, never relative to the final tangent. Okay, so just make note of that. I've seen this, people make mistake that beyond the point of PVI, they start defining the y value from this. But that's not how it works, because if you look at the formula for y, it's ax squared. A is a constant, and x squared is always a positive number. So as you move forward in this trend, this distance always has to increase. So that is your clue to note that if you start noting this from the final tangent, you're basically making a mistake, because that value would start to go down beyond PVI. But in this value, according to this formula, never actually start to decrease. It always increases. So always define that from the initial tangent. Okay, so y equal to ax squared, and then E is equal to a over L over 2 squared. Basically, you start plugging in the value for x's and start getting the value. So if you want to find the value for E is kind of defined right in the middle. The x value here is L over 2, because as I told you, most curves are defined as equal tangent vertical curves. So that's going to be L over 2 value. So you plug in x is equal to L over 2, you get the E value. That's defined right here in the figure. Small r, let's look at small r. It's the rate of change of grade. It's g2 minus g1 over L. And that's the beauty of the parabola, because that value is always the same. And then K is the rate of vertical curvature. Capital K is the rate of vertical curvature. And it is defined as K is equal to L over capital A. Okay, L over capital A. And you might be wondering why they don't define capital A anywhere in this figure. Okay, and they don't define it because they define the A value with the side distance formula, which we haven't yet learned, because I want to make sure that we learn the fundamentals first. But this would be a good point for us to sort of pick up on that discussion, where K is equal to L over A, L over capital A now. And capital A is basically defined on the previous page. So I'm going to go back to that. So this is page 167. But capital A is defined on page let's see where that is defined. Capital A is defined on where they provided the basic formulas on page 164. So if you go back here and take a look at absolute value of algebraic difference in grades. So capital value is defined as absolute value in algebraic difference in grades in percentage. This is very important. The unit here is percentage. I cannot emphasize the importance of making sure that your unit is correct. So I will just make a note here that if I go back to my formula here, if I'm trying to figure out the value for K for any vertical curve, this A is defined on page 164, and it's defined as absolute value of algebraic difference in grade as a percentage. Now let's take an example. I'm going to define a vertical curve here. Maybe I'm going to do that on a separate sheet of paper, which I haven't yet used, but I think this is time to use it. And they haven't paid any money for this, but this is an old Homewood Suites Hilton. It could be an example of product placement. But let's talk about this. So let's say, how do I define this A value and then use rate of vertical curvature based on that? So what I'm going to do is I'm going to have define a vertical curve. So let's say my vertical curve is like this. I'll use a different color here. And then let's say this is my PVC. Okay. Let's say this curve is plus 3%. And then this grade is minus 2%. So this is a crest vertical curve because G1 value is greater than G2 value. So A value in this example would be the algebraic difference measured as a percentage between the two grades. So basically you're measuring what is and it's the absolute value. So it doesn't matter the sign. Absolute value of change in grade. Okay. And that comes to plus 3 and minus 2. So that will be, in this case, would be 5%. My change, I don't have to do plus 5 because obviously I'm measuring absolute value. So that will be positive. So A value in this case would be 5%. Now let's think about some other examples. So obviously this is a crest curve. Now let's talk about this example where it's a sag curve. Okay. So let's talk about the sag curve. So let's say that my curve looks like this. My two grades look like this. And my sag curve is something like this. And let's say this grade is minus 1%, not drawn to scale obviously, and then this is plus 3%. What is the absolute value of change in grade here? So in this example, A value would be the difference in grade. So it will be G2 plus 3 minus 1, an absolute value of that. It's 4%. Remember, the value here of capital A is always measured in terms of percentages. Okay, so that's how you will define these values. Now, one thing is that the formula that we came up with where we were looking at this, why we wanted to kind of get this formula is we wanted to define the value for A because that relates with our what we call the K value. It's the rate of vertical curvature. Okay, so what does that mean actually? So rate of vertical curvature is not a terribly clear way of saying this. A better way to say this is what I'm going to write here. What is the rate of vertical curvature? It's a good sort of more clear definition of this is length of vertical curve required to change the grade by 1 percentage point. Okay? Change the grade by 1 percentage point. Why is this a good definition? So let's think about these examples that we covered earlier. So remember this definition of this is the K value is defined as length of vertical curve required to change the grade by 1%. And that K value is defined as L over A. So remember, I told you that the length of a vertical curve is defined along the horizontal plane. So let's say the length of this curve, just to take a quick example, is 600 feet. So what is happening in this curve is a change of grade from plus 3 to minus 2. So you're essentially changing the grade by 5%. Okay? And you're doing this over a length of 600 feet. So if you want to figure out how much is the length of curve required to change the grade by just 1%, you will go and get it as 600 divided by 5. Because remember, A value was 5%. So you will do 600 by 5, and your value will be 120. So that means if you go 120 feet on this curve, you change the grade by 1%. Okay, so what happens here is that, so you can almost figure out if you go to any point on this curve, what will be the grade. So let's say if you go 200 feet along this curve, what will be the slope of the tangent at this point? You can figure this out. Does that make sense? To be able to figure this out, how would you figure it out? You can say that the K value is 120 feet. Okay, so K value means 120 feet, means the length of vertical curve required to change the grade by 1% is 120 feet. Okay, so let's say you go to a distance, not 200 feet, I'm going to just make the calculation easier. So let's say you go 240 feet along this curve, 240 feet along this curve. What will be the length of the tangent here? So if you go 120 feet, you change the grade by 1%. If you go 240 feet, you will change the grade by what percentage point? You will change the grade by 2 percentage points. So by this time, when you hit this point on the curve, you would have gone from plus 3%, you would have changed it by 2%, and you would, the grade at the tangent here would be 1%. Similarly, and this is very important because there might be some examples related to this, you can also figure out what will be the length where you hit the grade of 0%. Okay, so the grade of 0% means the vertical curve here will have a 0 slope. The tangent will be sort of like a 0% tangent. And that 0% would be a point here. If the slope is 0%, that means how much have you changed the grade by? You have changed the grade by from plus 3 all the way to 0. So that means you've changed the grade by 3%. How much length would you need to do that? You will need, to change the grade by 1%, you need 120 feet. To change the grade by 2%, you need 240 feet. To change the grade by 3% and basically making go from plus 3 to 0 is 360 feet. Okay? So that means if you go 360 feet along the curve, the vertical curve there would be flat. And these types of examples are very important because if you go do this calculation using the offset equation, it'll take you a lot of time to solve it. But if you use the K value, you can arrive at the point where the curve is flat very, very quickly by figuring out what is your initial grade. To go to 0, how much change would you need? And then if you know the K value, you can quickly derive what is the length that you require to go from whatever grade the initial was, and then you could do that same thing. Now let's do the same quick example. Is if the example, I'm going to try to solve the problem. At what point the sag vertical curve is flat, okay? And obviously you need to know, so this is PVC, this is PVT, and let's say the length of the curve, if you project it on the horizontal plane, is the same as 400 feet. The length is 400 feet. So it's a 400 feet curve. It's going from -1% to plus 3%. And your question is, at what point the sag vertical curve is flat? So at what distance from PVC is the sag vertical curve flat? Now this is a very important question, but it can be very easy to figure it out. First, what you need to do is figure out what the K value for this curve is. So you figure out the K value by looking at, first figuring out the A value. A value, as we figured out, is 4% because you're going from -1 to plus 3. So you're changing the grade by 4%. So your A value is 4%. Your length of the curve is 400 feet. So your K value will be 400 divided by 4. And obviously I've chosen these values to make the calculations much easier. So that makes it 100. So K value is 100 feet. What does that mean? That means to change the grade by 1%, you need to go 100 feet along the X direction. Okay? And because you need to go 100 feet in X direction, you have to go to the flat point on the curve To go to the flat point of the curve, your slope at the flat point would be grade at flat point is 0%. That means you're changing the grade from -1% to 0%. So you're instituting a 1% change. And how much length do you require to make a 1% change? It's 100 feet, because that's the definition of K value, right? So that means the curve is flat at 100 feet. Okay? So one station away, because remember, I told you stationing is measured in 100 feet. So that's another concept that you could relate to it. At one station away from PVC, your curve is flat. And obviously that one station away will come much sooner here. Okay? So that's basically the idea of how this formula that is given here, K and K equal to L over A, could be very helpful to you in figuring out where the vertical curve is flat. And you can do so very, very quickly, but you have to know the concepts involved here. And you have to know that when the curve is flat, the grade is 0%. And then how do you figure out the rate of vertical curvature? And you have to know the clear definition of it. It's the length of the vertical curve required to change the grade by 1%. And that's the definition of it. And A value is defined in page 164. Okay. So I'm ready to hit the side distance formula, but I would appreciate if there are any questions associated with this discussion so far.
Just to be clear, have you gone over the format of stationing?
Okay, so yes, I haven't gone over the format of stationing yet in terms of the vertical curve. I didn't mention that the stationing is defined as 100 feet. And
I mean the 0, 0 plus 0, 0. Because that
I haven't gone over that, so I will go over that when we do some example problems, because that's just the easiest way to do that. So I will, when we work on some example problems where we're looking at some stationing values as given, I will make sure that we learn to interpret those things.
Okay, thank you, Dr. Pandey.
Thank you. Okay, so let's see. So one thing that I do want to do now is kind of go back to the discussion on side distance now. So I want to go back and look at some side distance issues. And side distance issues first were introduced to us when we were talking about vertical curves and horizontal curves, and we didn't get a chance to discuss those before. And this is where those are at. Now, the side distance formulas that are given here on page 165 of your manual. And there are different formulas for crest vertical curve and sag vertical curve. So it's very important for you to figure out that you are applying the correct formula for sag or crest vertical curve. Now, when you apply these formulas, you could be looking at these problems in two different circumstances. One could be the S value, which is the side distance value. So they are all dependent upon the side distance value. And then L is the length of the curve. So there could be two different scenarios that you might be evaluating these things, where S is less than or equal to L, or where S is greater than or equal to, or S is greater than L. So there are two different scenarios. And those two scenarios arise from the fact that when you're navigating, when as a driver, somebody's navigating the crest or sag vertical curves, there could be different situations that arise. There could be different situations that arise. So let's kind of go over those situations real quick. So when you're dealing with a crest vertical curve, so I'm going to talk about a crest vertical curve. And let's say the crest vertical curves look like this. So this is your initial tangent, this is your final tangent. Okay. And then this is your PVC. This is your PVT. Okay. Now, as you're navigating the curve as a driver, there could be two relevant side distance situations here. And the problem with side distance comes from the fact that there is a hill here, right? So there is basically a crest vertical curve. And remember, this is profile view, so you're looking at it from a side angle. And as a driver, when you approach this, your eye height will be over here somewhere. Okay, and you might have to look at an object that sometimes might be located beyond the curve, and there could be a situation where this hill of the road blocks your view. And anytime there is a blockage like this, agencies will put warnings like hill blocks view, or so those types of warnings are placed if that is the case. And then this is clearly a situation where, as you move forward, you will be able to see beyond the curve. So you could have a situation where your critical dimension of the object height, so basically around the bend is basically, this is based on the object that you need to see. And then this is where the driver eye is located. And then all those terms basically appear in the formula, the H1 value and the H2 value, H1 and H2 value. And again, if you're in a situation where S is greater than L, then H1 and H2 values are also defined. And then these are basically based on the fact that whether the limiting situation arrives when you're outside the curve, or sometimes the limiting situation may arise when your driver is already inside the curve and it's trying to locate the object. So when the hill is particularly steep, you might be in a situation where it's a short curve and that's what's blocking the view, and S is less than or equal to L. Now, the S value, if you look at all these values that are defined in these formulas, this capital S value, they're all defined on page 164. Okay, so let's go back and take a look at what these different values look like. S is less than or equal to L, and S is greater than or equal to L, and so on and so forth. And remember, this is the generic formula. This is the generic formula. But if they don't give you some values like H1 and H2, which I'm going to define in a second, if they don't give you any value, you can use the standard criteria value that are defined in the AASHTO Green Book. And I know Caltrans uses some different values sometimes, but in the FE exam, that is not relevant right now. We'll just go by the AASHTO Green Book, which is the National Design Guideline on streets. So basically, this bottom formula is a special case of the top formula where you plug in H1 equal to 3.5 and H2 equal to 2 feet. And then here, the same thing for S greater than L equal to formula where you replace H1 and H2 values with these given values. But these are the more generic formula that you will apply if you're given any H1 and H2 values here. Now, so let's take a look at what these values look like. H1 and H2 are defined as height of the driver's eye above the roadway surface, and H2 is the height of the object that the driver needs to see above the roadway surface. So those are your H1 and H2. Capital L is the length of the curve in feet. Okay, so length of the curve, again, for vertical curves, that's defined along the horizontal plane. So make sure that you measure the horizontal distance. That will be your length of the curve. And in design problems, this is what you're really after. You're trying to find the L value, capital L value. And so if S is less than L, I already defined the capital A value. That's the percentage change in grade, the absolute value of that. And this S is the stopping sight distance. Now, how do you find this S? This S will be based on the design value, and you will get that S value using this formula. S, capital S, if you look at the formula here, I don't recall that they define S here. So they don't define the S value here, but S value is essentially the stopping sight distance that you need to be able to stop on that curve. So obviously, as the stopping sight distance increases, what happens to the L value? It changes S squared. It's a formula, it's an empirical formula that changes by a factor of S squared. So as you increase the stopping sight distance, which you can obtain using this formula, but before you go ahead and apply this formula, be careful and make sure that you take a look at the problem carefully, because in some cases, the problem might specify that value. So you can either get that value from this formula based on the design speed, or you can get that from the given problem. So that's S is the stopping side distance. But there is one sort of critical consideration here that appears when you're trying to solve problems like this. Now, these problems actually are going to be a little bit time consuming in that you will have to know what is S, and sometimes they could be time consuming because you don't know exactly before you've solved the problem which of these formulas apply, because they are actually going to be asking you for length of the curve, for example, and you don't know whether S is less than L or S is greater than L because you don't know L yet. So how do you approach this problem? You approach this problem more iteratively, and the way you approach it is basically you figure out, okay, I'm going to apply this S less than or equal to L formula. I'm going to figure out my L, and I'm going to check back with my assumption. If S is indeed less than L, then I'm done with the problem. But if my S is greater than L, then I'll go back and apply this formula. Okay, so that's how you sort of have to iterate some issues here. Now, we'll work out some problems on that, and that will make it clear. But I want you to make sure that you understand that this type of problems would be a little bit time consuming. And also, it's okay if it takes some time and then the answer that you get by assuming one of these formula doesn't make sense, because that might be by design, and you actually might have to do the iteration where you figure out the formula S less than L first, you apply it, and then if it doesn't work, then you apply this formula, and then that will work. Okay, and then there are different formula for crest vertical curve. Remember, the condition for crest vertical curve is G1. Crest vertical curve happens when G1 is greater than G2. And then sag vertical curves happens when G1 is less than G2. Okay, so remember that always. So crest and sag vertical curve conditions. And again, we're not talking absolute values, we're talking about the actual values. So a positive grade is always greater than a negative grade. If G1 is less than G2, it's going to end up with sag vertical curve. So make sure that you're applying the correct formula from this. Now, why are those two formulas are different? You might be wondering, why are those two formulas different? And that kind of brings you back to that discussion that we were having before. If I try to draw up a sag vertical curve here, so this is your crest vertical curve, this is where the hill blocks you. But if you talk about a sag vertical curve, there's nothing to actually block the view. So you might be wondering, like, so on a sag vertical curve, this is the vehicle traveling this way, and then there might be an object over here. So there's no blocking the view here. So you might be wondering, why is side distance even a problem here, right? So because there is no hill to block view, as was the case in a crest curve, hill might block the view, and then you might not be able to see around the vertical curve, around the hill. But here, there's no problem. I mean, as a driver, you can see basically any type of distance beyond the curve, right? So what's the problem? And this could be a good conceptual question for your FE exam. So why is there even a side distance consideration for sag vertical curves? Why do we even need these formulas that are here? And why do we need these formulas is that not for the daytime driving conditions, because in daytime driving condition, this is never a problem. But in a nighttime driving condition, what might change is that your headlight might only illuminate a certain distance of the curve. And these formulas are in fact derived based on standard headlight criteria. So you could see underneath the formula, they note that this is standard headlight criteria. So they make some assumptions about what those headlights look like. And obviously, there have been some vehicular design improvements, and some of these formulas might become too conservative at this point. But again, we don't have to go down that discussion for the purposes of the FE exam. We should be okay here. But again, you have S less than or equal to criteria, you figure out, and all these things we have already talked about, capital A, S, and S. So again, the object height doesn't figure into this because they've already accounted for the standard object height and standard criteria. And then length would be this. If you're talking about S greater than L, again, you wouldn't know at the beginning of the problem which formula to apply, so you'll apply one of them and see if your assumption was correct. If it was incorrect, then you'll apply the other formula. So that's how that works. Now, there might be other considerations on the sag vertical curve because there might be, this is the standard headlight criteria, then because there are some criteria you have to make sure that the minimum length is provided based on the riding comfort as well. So there is another criteria based on riding comfort. You want to make sure that the dip is not very, very steep in nature. So you basically calculate L value based off of that. And then sag vertical curve L value is also provided if there is an overhead structure that might potentially cause some problems. So based on adequate sight distance under an overhead structure to see the object beyond the sag vertical curve, if an overhead structure might be a problem, then this is the formula there. So what you're seeing here is crest vertical curve, only the hill could block the view. But in a sag vertical curve, problem could be basically 3 different criteria might present you a problem. So you might find a minimum value of length based on 3 different formulas. So how do you choose between them? So what you do essentially is that you apply all of those formulas and you make sure that you provide the maximum possible length from those formulas. So all of these formulas will be giving you the minimum required length, and whichever gives you the highest value, you use that length for your design, because that will address all 3 of the criteria. So all these formulas are essentially giving you the minimum length of the curves required, and you want to make sure that the minimum criteria is met based on all 3 things. So you provide the highest value that you get from the sag vertical curve calculations using these 3 criteria. Okay? For crest vertical curve, there is only one criteria, that's sight distance, being able to see beyond the hill. So that's not a problem. But for sag vertical curves, all 3 criteria apply. And based on all 3 criteria, you have to provide the minimum length of the curve. And again, from a design perspective, larger length of the curve is better. Why larger length is better? Because then that means you're providing longer distance for the drivers to be able to change the grade. And that's what provides the key thing. So I will stop here for just 1 second and ask if there are any questions about this. I know this is a lot to cover here. So I would not be surprised if there are some questions here, but if there are some, I would welcome them at this point. And again, some of these things would be clearer if you go back and try to work out some examples, which we'll also do as part of these sessions once we are done with the theoretical discussion.
There are, yeah, there are no questions in the chat right now.
Okay, perfect, thank you. So, and again, a lot of things to cover here. All the formula values are provided. Just make sure that the crest vertical curve has only one value to figure it out. Just 2 different considerations, 2 different criteria, S less than or greater than L. But the sag vertical curve has 3 different criteria. Again, 2 different set of formulas for those considerations. But the riding comfort is only 1 criteria. So just kind of making sure that you understand how these formulas are provided, and all these values you can figure they are provided. Okay, so working out some examples would be the best way. So if you really want to know if you've understood it, go back and try to work out some examples. If you can work those out, that's great. But if you can't, then you might want to have some refresher information from this. And again, you'll find this in your introductory transportation class under the highway design criteria. Now, for horizontal curve, things are slightly different. There's a lot going on horizontal curve. But again, in horizontal curve, things are different. You look at from the top view perspective, and then those formulas are given here. So there are things here that you need to sort of worry about. For horizontal curve, there is the idea of the side friction factor. That is different than the longitudinal friction factor that I talked about at the very beginning when we were talking about the stop side distance formula. But the side friction factor is the sideways movement, is about the lateral movement, okay? And then this is basically the super elevation calculation. So when super elevation calculation is very important, and now remember, whenever you're looking at any kind of roadway cross-section, roadway design, you're talking about 3 things. You're talking about plan view, you're talking about the profile view, okay? And then you're talking about cross-section. Okay? So when you talk about the plan view, that's your horizontal curve criteria, basically a bird's eye view. You look at things from the top. Okay? In the profile view, that's very important for the vertical curve design. That's what we talk about when the drivers are trying to navigate that profile view going up or down, things like that. And the cross section is when you're trying to navigate the roadway, how are the lanes situated? Now, this cross-section design is something that we haven't yet talked about, but it's very important, obviously. And in cross-section is different for the roadway section. The cross-section design is different. And basically, you're looking at into the plane of the paper, and then this is like the width of the roadway. You're looking at the width of the roadway. And the typical section of the road looks like this. Okay? And this is what we call a typical crown section. Typical crown section will have basically drainage as its criteria, and the side slope will be about 2%, 2%. Now remember, I'm not talking about a vertical curve or a profile view. This is the cross-section view I'm talking about. So this is what you're looking at is roadway's width. So basically, this might be a lane here, and then there might be like a shoulder at the end of this. So this is basically representing the shoulder, and roadway is sort of going into the plane of the paper here. So when you're driving on the road, you'll basically be driving into the paper. So and then this would be the lane width. So this is one lane width, this is another lane width, and then you might have some shoulder. So this is like 2 lanes here on the cross-section side. So you're looking at the cross-section. So as I said, the typical cross-section is about 2% grade on either side from the center line of the road. And that is provided for drainage purposes. And this is what works when the roadway is basically without any curvature. So any straight section of the road will typically have this type of a crown section, a typical crown section. Now, when the roadway curves, so I'm looking at, when the roadway curves, what happens is that you need to, when the roadway is curving, so I'm going to look at now, so this is going to get a little bit confusing, but let's talk about, let me show you the plan and top view. When the roadway actually curves, let's say I'm looking at this. So you have a road that goes from going like this, and you have a circular curve, and then the roadway goes like this, and then it becomes a tangent again. So what happens is that your roadway is sort of turning here. And you're looking at it from a bird's eye view now, and the roadway is sort of turning. Now what you're doing is that drivers were moving at basically an infinite radius. A straight line is infinite radius. So the rate r equal to infinity, right? So it's basically a straight line. And then the r becomes a smaller value. Okay, so r will be, let's say, a certain value of, I'm going to say 1500 feet radius curve. Okay, so this is a 1500 foot radius curve. So what happens is that when you're navigating a circular curve, you need to be on the road. There's a force that basically you need to make sure that to be able to be on that circular road so that you can navigate that environment, you need a net force inward that keeps you on that curve. Okay? You need a net force inward that keeps you on that curve, and that force is defined as mass times v square over the radius. Okay? Mass times v square over the radius. Right? And typically we define this radius, and you can see this force is going to be higher if your speed is high, because it's so this is your force required is mv squared by r. To be on that circular path, you require a force that pulls you inwards, and that force is proportional to the mass, which we can, but the acceleration that you need is proportional to the speed squared, and then inversely proportional to the radius. So as the radius is higher, you don't need as much force. So obviously if the radius is infinity, as was here, you don't require any force inward. So we can basically rely on this typical crown section and on the cross-section side of things. But if I try to draw the cross section, I want to be able to pull the vehicle inward. So what my cross section looks like is what we call the super elevated cross section. And the super elevated cross section will basically have the outer edge of the pavement. So this is the center line of the road. Again, I'm drawing the cross section now. So you're looking at the cross section view, looking at the cross section view. The driver now drives, I'm sorry, there was a little mishap here. So let me, got too close. Sorry guys, let's see here. And I'm trying to get that at the same angle. Give me 1 second here.
Yeah. No worries, Dr. Pandey. We can always just cut this part out of the video.
Oh, that'll be great. Yes. So let's see. So sorry for the mishap here, but what I was trying to point out, is that I'm now looking at the cross-section view again. And that cross-section view, basically, this is the center line of the road. So I'm going to just call it CL, the center line of the road. That goes into the plane of the paper. Okay. And I'm going to raise my outer edge relative to the inside edge of the road. Now you can see that if you're talking about this force that was required, it's proportional to the V square and then inversely proportional to the radius. So the more inward you are, the closer to the center you are, the larger the force that you require. Okay, so typically what we do is we look at the inside lane radius, that's our critical radius. So the inside lane will be located here, and we raise the outer edge of the road. And then this slope is typically on the rural road, that slope could be as high as 6% to 8%. Now, if you want to visualize what the roads look like, think about, even if you're not a NASCAR fan, think about, or maybe check out some videos of NASCAR. The drivers are driving at a very, very high speed, and the turns are very sharp. And on those sharp turns, what you notice is that the outer edge of the pavement is raised very, very high. Obviously, on the roads that Caltrans or the state highway agencies would design will have no slope, no cross-section slope that look like the NASCAR road. But that will help you visualize what kind of super elevation that we are talking about. So typically on a public roads, the super elevation could be as high as about 8% on rural road because the speeds are higher. And we design that 8% super elevation. But on urban roads, we typically limit ourselves to 4 to 6% because the urban roads might have congestion and they don't have as high a speed, so they don't require as much of a super elevation. Okay? Now the question is, the more super elevation you can provide, that means you can provide a smaller radius for the same design speed. Okay, because this slope can basically pull your vehicle inward and provide that inward force that the vehicle needs to stay on that lane. Okay, and how do you actually figure this value out? So this is basically conceptual consideration around super elevation. But how do you actually figure this out is the formula given here. So side friction factor based on super elevation can be used, and this will typically be given to you in the problem. So you can figure out, using this formula, you can figure out how much E do you need. E is the super elevation. And if you want to look at where E is fine, so all these values are from page 164. So if you go back to page 164, we can figure out small e, small f, and capital R. Small f is the side friction factor. Small e is the super elevation as a percentage. Again, units are very important. So if I say that super elevation is needed at 8%, so then you will put it as 8 here. Okay, and then V is the design speed, capital V, so you'll enter that in miles per hour, and R is the radius in feet. And again, the units are consistent, so you can plug in V in miles per hour, R in feet, you'll be fine, because that's what these V are, and you just go back and page 164. So you can solve for any value here, either for E, for small f, for capital V or capital R. Any of these formulas could be worked out in the form of problem. So you could figure out how much have to be the side coefficient if you're providing a certain super elevation and you know the design speed and radius, or you might be asked to figure out what is the minimum radius that you need to provide, or what is the maximum design speed that you could provide on a certain road given certain values. Okay. Now, one thing that I told you that we might not be considering this, at least in the design purposes, when we were discussing the horizontal curve design. I talked about the length of the spiral curve. That's the transition of the recital curve. This is just a simple formula. I don't expect them to be able for you to be asked to design a complete spiral curve, but they might ask you for how much transition length might be required to go from a straight section to a fully circular curve section. So LS would be 3.15 times V cube over RC, and all these parameters will be given to you in the problem. C is something that is given here, rate of change, increase of the lateral acceleration, use 1 feet per second cube unless otherwise stated. So this will be a given value. So if they ask you for a problem on spiral curve, this will be very plug and chug kind, and you will be able to figure that out. I do not expect you to be able to design the full spiral curve for the FE exam. And then this, I'm going to stop here right now because the next topic that they talk about is the side distance on the horizontal curve. That does require for us to learn some things about how the object height, or sorry, object location relative to the horizontal curve affects it. So we will stop here right now and pick up in our next video how we apply and learn about this formula. And that will basically complete our discussion on the highway design portion of this discussion. So I will pick it up from side distance consideration. That will be a 15-20 minute lecture on its own. So we'll pick it up from there, and I will stop here for now. Thank you, guys. Any questions so far?
No questions, but thank you for doing this, Dr. Pandey.
Absolutely. It's my pleasure. So I'm going to stop it here, recording, and then we can chat for a little bit.
All right.